So, in the last lecture we were deriving conservation equations for mass and energy conservation. Okay. So, conservation equations. In a Cartesian coordinate system. Three orthogonal coordinates, okay, in a Cartesian coordinate system, x, y and z, all perpendicular to each other, and we had written a balance equation for a cubic differential volume, okay, of sides delta x in the x direction, delta y in the y direction, delta z in the z direction. Okay. So, the balance equation basically was that the change in mass in the differential volume in a time delta t is equal to the mass in minus the mass out plus the rate of production of mass within the time delta t. So, this balance condition for this differential volume, you write down the balance over a time delta t, divide by volume, divide by delta t, and then take the limit as delta x, delta y, delta z and delta t all go to 0, okay, and you get the conservation equation. Partial c by partial t plus the divergence of, sorry, plus the source. Okay. So, that was the conservation, the equation that we had derived, okay, for this differential volume, and we saw that this can also be written as partial c by partial t plus the divergence of v times c is equal to minus the divergence of j plus s, where the divergence dotted with a vector was equal to partial c by partial. Okay, which is okay, that is the divergence of a vector, that is the definition of the divergence. The constitutive relation was j is equal to minus d times the gradient of the concentration. Okay, that was the constitutive relation. Fick's law for diffusion written in vector form. Okay, Fick's law for diffusion written in vector form, where the gradient of the concentration is equal to Ex partial c by partial x plus Ey partial c by partial y. Okay. So, this thing here is the divergence, this is the gradient. Okay. This thing here is what is called the gradient operator. Okay. Okay, this is called the gradient operator. Okay. So, those are the conservation equations, and if we substitute the constitutive relation into the conservation equation, we got, okay, the resulting conservation equation as partial C by partial T plus del dot V. Okay, is equal to the divergence of d times the gradient of C plus S. This is in vector notation. Okay. This is in vector notation. Okay. And if d is independent of position, okay, if it is a constant, then we can take it out of this. Okay. D del square C plus S. So, let me just write it once again. Where this del square is the Laplacian, okay, which is the divergence of the gradient. Okay. And if you expand it out, it is easy to see that this is partial by partial x square plus partial by partial y square plus. Okay. So, that is the expression. Okay. The important point to note in all of this is that the equations written out in component form, okay, these equations written in component form will change when you change coordinate systems. For example, if you change the axis from x, y, z to x prime, y prime, z prime, then the equations will change when written in component form. However, the equation when written in vector notation does not change, okay, regardless of how the coordinate system changes, because all of these terms here, the velocity vector, the flux vector, the concentration scalar, they all have a value and a direction in the case of vectors, which are independent of the coordinate system used for analyzing the problem. Okay. So, the equation written in coordinate form does depend upon the coordinate used. The equation written in vector form will not depend upon the coordinate that is used. Okay. And then I had also shown you that the substantial derivative okay, if I have some velocity field and there is volume of fluid that is being convected along with this velocity field. Okay. So, that at the time t the volume is located at the location x, and at the time t plus delta t the volume is located at the location x plus delta x. Okay. Okay. At the time t plus delta t the volume is located at the location x plus delta x, where delta x can be written as delta t times v. Okay. The product of the velocity and the time interval, the vector velocity and the time interval. Okay. Is the vector displacement with components delta x is equal to Vx delta t, delta y is equal to Vy delta t, and delta z is equal to Vz delta t. These are the components, okay, of the displacement vector. Okay. The substantial derivative is defined as the derivative in a reference frame that is moving with the velocity. Okay. So, there is a point at x at time t, okay. It shifts to some other location x plus delta x at time t plus delta t, okay. And the substantial derivative of the concentration field I had derived in the last time, dc by dt is equal to limit as delta t go 0 of c at x plus delta x and this can be written as using chain rule for differentiation and the substitution for the components, and the substitution for the components. This can be written as Vx partial c by partial, first time derivative that is it in component form. And if I were to write the same thing in vector notation, I will get partial c by partial t plus v dotted with grad c. Okay. And if I substitute that into the conservation equation, dc by dt plus c times the divergence of the velocity is equal to the divergence of d grad c plus s. Okay. And if the diffusion coefficient is a constant, this is just equal to d del square c plus s. Okay. Okay. So, these are the conservation equations in a Cartesian coordinate system and in a vector form. The conservation equation in other coordinate systems in the vector form will be exactly the same. Constitutive relations will also be the same. Okay. So, let us look at another coordinate system, and that is the spherical coordinate system. We had seen this before when we did curvilinear coordinates. This is used, for example, for a spherical geometry. If you have to apply boundary conditions on a spherical surface, these are applied on a surface whose distance from the center is a constant. Okay. That is, the distance of a spherical surface from the center of the sphere is always a constant. Okay. So, one of the coordinates, if you have to select one of the coordinates such that the distance from the center is a constant, then that coordinate has to be the distance from the center. Okay. So, one of the coordinates in a spherical system is the coordinate r, which is the distance of a point from the center, okay, of the coordinate system or the sphere, as the case may be. Okay. However, this is only one coordinate. Okay. There are three coordinates which have to be specified. Okay. In a spherical coordinate system, the other two coordinates are theta. Okay. This is called the azimuthal coordinate system, azimuthal coordinate theta. It is the angle made by the displacement vector with the z axis. Okay. The angle made by the displacement of the location x from the center. Okay. So, this vector displacement is x. That vector makes an angle theta with the z axis. So, that is the second coordinate. Okay. So, therefore, okay, the height of this location above the xy plane, which is the same as the angle theta. Okay. The height of this location above the xy plane, which is the angle theta, has to be r times cos theta. Okay. And the projection of this displacement vector onto the xy plane, that will have length of r times sin theta. Okay. So the displacement vector has length r. Its projection along the z direction has r cos theta, where theta is the angle made by this displacement vector with the z axis, and the projection of the displacement vector onto the xy plane is what is called his r sin theta. The angle made by this projection with the x axis is the third coordinate. Okay. It is called phi. It is the meridional angle. Okay. The meridional angle, the angle along the meridian around the axis z is called the meridional angle, and that is phi. Note that theta is the angle made with the plus z direction. Okay. So, theta is 0 when for any location on the plus z axis. On the minus z axis, any location theta has to be pi, because the angle made is pi. Okay. So, therefore, okay, the distance r from the center is a distance. Okay. It always has to be greater than 0, and theta has to vary between 0 and pi. And the angle phi, which is the angle around an axis. Okay. Around the axis you can go an angle which is total of 2 pi. Okay. When you go one circle around the axis, the angle is 2 pi. So, phi varies between 0 and 2 pi. Okay. So, these are the three coordinates in a spherical coordinate system. The distance from the center r, the angle from the plus z direction theta, and the angle from that the projection makes from the plus x direction, that is phi. Okay. So, therefore, r has to be equal to the distance, which is square root of x square plus y square plus z square. The angle theta, okay, cos theta is equal to, okay, z by r. Okay. Cos theta is equal to z by r. Okay. Z divided by the distance from the origin, that is cos theta. Positive if it is above the xy plane, negative if it is below the xy plane, and sin theta is equal to this projection. Okay. This projection divided by r. Okay. Or alternatively, tan theta is equal to z by root of x square plus y square. Okay. That is the that is the relationship between theta and the Cartesian coordinates x, y, and z. And similarly, tan phi is equal to y by x. Okay. Okay. Because phi is the angle made by the projection onto the xy plane. So, x is basically, okay, x is equal to root of x square plus y square into cos phi, and y will be equal to root of x square plus y square into sin phi. Okay. So, tan phi will be equal to y by x. Okay. So, that is the relation between that is the spherical coordinates expressed in terms of the Cartesian coordinates. Okay. The converse, I can write, okay, x is equal to, sorry, r cos theta, x is equal to r sin theta cos phi, and y is equal to r sin theta sin phi. Okay. So, these are the relations between the Cartesian coordinate system and the spherical coordinate system. Okay. These coordinates can be related to a more familiar example of the geographic coordinate system on the Earth's surface. Okay. Okay. So, if you recall the Earth's surface, okay, surface has constant distance from the center. Well, not quite a constant, it is slightly flattened at the poles and slightly larger in diameter at the equator, but to a good approximation it is a constant distance from the center. Okay. And you all know the sectioning of this in the familiar example of the latitudes and the longitudes. Okay. So, for example, the equator, okay, the equator has a constant, okay, it is 0 degree latitude. Okay. So, if I use the geographic coordinates as phi, okay, as distinct from this phi that I am using here. Okay. So, this thing is equals 0, okay, that is the equator. Okay. And then you have the 30 degree line, okay, the Tropic of Cancer and the Tropic of Capricorn, where phi is equal to pi by 6. The 60 degree line, okay, the Arctic and the Antarctic circles, here phi is equal to pi by 3, and then at the poles phi is equal, okay, at the poles. Okay. And in the southern hemisphere you will have, it will be negative, okay, minus pi by 6, then you have minus pi by 3, and here phi is equal to minus pi by 2. Okay. These are almost the same as the azimuthal angle theta. Okay. On the north pole the azimuthal angle theta has to be equal to 0, angle from the z axis, and the z axis is the line through the north and south poles in this case. Okay. If we consider z as the direction vertical, okay, along the axis of rotation, if we consider the z direction as along the axis of rotation, theta is equal to 0 corresponds to the north pole in the geographic coordinate system. Okay. Then I have theta is equal to pi by 6, theta is equal to pi by 3, and the equator is theta is equal to pi by 2. Okay. The geographic coordinate 0 is equivalent to theta equals pi by 2. Okay. And then over here you have theta is equal to 5 pi by 6, theta is equal to 2 pi by 3, and finally here you have theta equals pi. Okay. So, therefore, the azimuthal angle that we are using here in the spherical coordinate system is almost identical to the geographic latitude. It is actually related by the relation theta is equal to pi by 2 minus this angle phi. Okay. So, that it is equal to 0 on the north pole, pi on the south pole, and pi by 2 on the equator. Okay. So, these two are almost the same. The angle theta is equal to pi by 2 minus the geographic latitude, okay, for the sectioning on the surface of a sphere. Okay. And the longitudes are exactly the same as the meridional angles. Okay. And the longitudes are exactly the same as the meridional angles. Okay. Okay, if we take along the equator, okay, if this is the x axis, okay, and this is perpendicular, the y axis, okay, along the equatorial plane, okay, then the angle phi is the angle made by any location on the surface, okay, the projection of that onto the xy plane with the x axis. Okay. So, this is the angle phi, okay, made by the projection, okay, this is x and this is y. If the projection of the position vector makes an angle phi with respect to the x axis, then that is the meridional angle phi. Okay. It starts at 0 meridian and it goes all the way around to 360, okay, or 2 pi. Okay. So, the angle phi, the meridional angle in a spherical coordinate system, is identical to the meridian in a geographic coordinate system, and the geographic latitude is related to the angle theta in a spherical coordinate system. Okay. So, that gives you a better visualization of the angles theta and phi in the sectioning of a spherical surface. Okay. Now, we have to construct a differential volume for doing a balance. At a location, okay, which is described by the coordinates r, theta, and the third one, which is the angle made with respect to the x axis phi of the projection of the unit vector, I am sorry, the projection of the displacement vector onto the x axis, onto the xy plane. The angle that that projection makes with the x axis is what is called phi. Okay. So, these are the three coordinates in this. Okay. Now, we have to construct a volume which has which is bounded by 6 surfaces, 2 each in each of the coordinate directions, separated by a small distance. Okay. 2 surfaces perpendicular to the r coordinate, separated by a small distance delta r, 2 surfaces perpendicular to the theta coordinate, separated by a distance, okay, which is corresponding to the increment in the theta coordinate, and 2 surfaces separated by an increment delta phi in the phi coordinate. Okay. So, let us construct those surfaces. Okay. So, 2 surfaces, okay, at the locations are, okay, in the radial direction. Okay. Okay, the inner surface will be at the location r minus delta r by 2, okay, the outer surface at r plus delta r by 2, okay, and the increment in the coordinate will be delta r. Okay. So, that is how you construct 2 surfaces in the r direction, which I will expand out here. Okay. There is a surface at r minus delta r by 2, surface at r plus delta r by 2, okay, with a separation delta r, okay, in the r direction. What about the theta direction? Okay. What about the theta direction? Okay. There will be 2 surfaces. Okay. The first one at, okay, theta minus delta theta by 2, okay, this one at theta plus delta theta by 2. Okay. And this separation between these 2 surfaces is not delta theta, because delta theta is an angle. Okay. The separation between these 2 surfaces has to be r times delta theta. Okay. The radius times the angle subtended in radians. Okay. That is the distance travelled when theta is increased from theta to theta minus delta theta by 2 to theta plus delta theta by 2. The distance actually travelled is r times the increment in the angle. Okay. So, that is the distance that is travelled. Okay. Similarly, in the direction perpendicular, okay, the phi direction. Okay. Okay. In the phi direction, there is an increment between of the angle phi, okay, between phi minus delta phi by 2 and phi plus delta phi by 2. Okay. The actual distance travelled is this radius times the subtended angle. Okay. The radius times the subtended angle. Note that this radius was r sin theta. Okay. The height was r cos theta, the projection on the xy plane was r sin theta. Okay. So, therefore, the distance that is travelled perpendicular to the plane along the phi direction has got to be equal to r sine theta delta phi. Okay. That is going to be the distance travelled. Okay. Okay. R sine theta delta phi, that is going to be the distance travelled. Okay. So, we will continue our discussion of a shell balance for a spherical coordinate system in the next lecture. Okay. So, I will continue this discussion then.